Hello everyone. So in this video I'm going to discuss about SystemVerilog interface in details with the help of a very simple example. So SystemVerilog interface works as a kind of bridge between the DUT and the test bench. And you can also say that between different modules and test bench. So it becomes very useful. So suppose there are multiple modules, uh, and each of those modules share some common signals. So interface can have all those common signals, and what you can do if you need to make any modification to those common signals, you just have to refer to the interface instead of modifying that signal in each and every module. So this makes it very easy, and also during the port declarations in the top level module, you just you just don't have to mention and declare those common signals again and again. So it just reduces the redundancy and some possible errors. So inside the post port list of those modules, instead of mentioning every single common signals, you can just go ahead and mention that interface. So let me demonstrate that with the help of a very simple example. And this example, I will be using the design of a D flip-flop. So first, I will go ahead and create the interface. So interface are kind of instantiated just like modules. So uh, they can have ports, and they can be defined separately from modules, and they can also be defined within a module. So let me go ahead and define our interface for our D flip-flop, which has a single bit input and a single bit output. So you just have to begin with the keyword interface, and then I will name my interface. So I am thinking of naming my design module to be DFF, which stands for D flip-flop. So I will just name it DFF underscore INTF, which stands for interface. So just like any other things in SystemVerilog like function and task or module, you just have to write and followed by the name of the keyword, which is interface in our case. So this is the format of interface, and inside the port list of interface, I will mention some signals. So for our case, I will mention the clock and reset signal. And I will mention the other essential signals for the D flip-flop inside the interface, and you will get to know why. So those other signals are obviously the input and output, and I want them to be of logic data type, and I will name the input as D in and the output as D out. So this is very simple. So uh, I just mentioned the clock and reset signal inside the port list of this interface because these signals will be connected uh, to the clock and reset signal, which are mentioned inside the test level, the test bench. So these signals are required to be connected to the test bench. And other than that, the other signals D in, D out, they are required to be connected with the design, the DUT. So this is just simple. You just have to mention all the signals, and the signals you want to connect with the test bench, you can mention it inside the port list. So now I will begin with my design. But before that, I will also introduce you with another concept, within another concept known as modport. And modport is basically used to mention the direction of each of the signals. So they can be used to restrict the direction of the same signals to different modules. So what I will do, I will just go ahead and use the modport. And to do that, you have to write the keyword modport, and then it should be followed by the user defined label or name. So I will name it dir, which stands for direction in my case. Now inside this, I need to mention the direction of each of the signals. So this is the view for the DUT which will be using that interface. So obviously the clock and reset should be of input, and also the DIN should be the input for my D flip flop in this case, and the output should be D out. So like this, you can mention many other mode ports. So suppose I can also write another mode port here, and I will name it reverse direction. And here I can just go ahead and uh, I can just make the D out, the D in to be as the output and the D out as input. So inside the port declaration of your DUT, you can just select a particular mode port. And depending upon the mode port you have selected, this particular direction will be assigned to its input. So interface is not just providing the signals for the DUT, it is also providing a mean of direction, and you can also restrict the direction for those signals to different modules. So I just wrote this as an example, and of course for my design of D flip-flop, I will be using this direction. So I will go ahead and declare the module for the D flip-flop. I will name it DFF, and inside the port declaration, instead of writing all the signals, I will just refer to the interface. And to do that, there are multiple ways. And those ways are the explicit declaration and the generic declaration. So for this example, and also for the mode port, there are multiple ways of uh, declaring them. So for this example, first I will just go through with the generic declaration, and then I will complete the test bench and run the simulation. Then after that, we will fiddle with the other types of declaration. So in generic declaration, you just have to use the keyword interface, just like there. And then you can mention any user-defined keyword. So for this, I will write pins. So this is user-defined. You can use whatever you want. Then of course, I will end the module, and I will put a label just for uh, some sophistication. So you will be referencing all the signals through the interface. So right now, what I will do, I will just go ahead and begin with the sequential logic of a D flip-flop. And since all the signals and the directions are mentioned here inside this interface, we don't have to declare any variable or signals inside this module. So I will begin with the always ff block, and inside this block, of course, I will use two signals. So I want this always ff to trigger whenever it detects any change at the pose edge of the clock. And since you are referring the interface, you are referring to the interface for those signals, you need to mention the whatever user-defined name you have used, and you need to mention that signal to access those signals. So here in this case, I will write pins dot, and inside pins, I will be referencing to the clock signal. So inside pins, I will write clock. And I want this flip-flop design to be to have a negative edge triggered reset. So I will mention neg edge of reset. And to access the reset variable or signal, I first have to write pin dot reset. So we'll begin. So if reset is high, oh wait, it's pins. So I should write pins here. Yeah. So if the reset signal is high, then the output should be 0, and the output is the out. So here, since you have mentioned the interface signals right here, you have to reference through every signals using this user-defined uh, user-defined port you have mentioned here. Else the out should be equals to, oops, the in. So I will just end the module. So this concludes our design. Also, I have to put a semicolon right here. So this concludes our design, which is connected to an interface, and we will move on with our test bench. So let's do it. So I will just go ahead and include the source file of the design, which is tff.sv. So inside this, I will only mention two signals which are kind of important to apply the stimulus. So these two signals will be the clock and reset. So now I will mention, or I will instantiate the interface. So to make an instance an instance of an interface, you just have to write the name of the interface. So it is same as the module interface instantiation. In here, what I will do, since the both of the signals are same to that of the interface, I will just use the wildcard port declaration. So this will match any port which are of same name. Now what I will do, I will mention my duty. So here, what I need to do here, I don't need to connect anything to the test bench. Rather, I have to connect it with the interface. So I will pass the stimulus using the interface to the duty. So duty will not have any connection to the test. So interface will be working as an intermediary. So, but I have one important thing to do. Since my declaration right here was the generic one, I need to mention that which mod port I am using, and I also need to mention the interface connected. So what I need to do, I just need to use the instance name of interface, which is mentioned right here. So this will connect our module to the interface. This is as simple. But since I also want to use the direction which are mentioned inside the mode port dir, I also need to connect this module to that mode port. So I will just write dot dir. So mode port is nothing. It's just a different perspective of those signals for different modules. So for some modules, the in can be input, and for the others, the in can be output. So now I will begin with my clock generation. And since clock is of logic type, I will first change its value to 0. Then I will use a forever loop, and after every a delay of 5, the clock will toggle. So I will write um, another initial block for the monitor that would continuously monitor the input and output, and also the time associated with the change in input and output. So first I will write the scope operator for time. Then I want to display the input, and I want to display the output. And here again, since the connection is between the the connection of the test bench is with the interface rather than the module, so we have to access the signals using the interface. So I will do that. And here we have to use the instance name, the in, the out. So now I will write uh, an initial block for the reset signals. So for my design, I think the reset is uh, active high. Yeah, if the reset is 1, then then the output will get 0. So first, I will just assert the reset. Then I want to repeat it for 3 neg of the clock. Then I will deassert the reset. So this concludes our initial block for the reset stimulus. And now I will begin with our stimulus for the D-in. So here I will provide 1 to the D-in signal. And since reset will be asserted for 3 neg clock ticks, this will not have any effect on the output. So I want it to repeat for at least 4 clock ticks so that it can be transitioned to the output in the next clock cycle. So I will just repeat 4 times at the negative edge of the clock. So what I am thinking of doing is that I will write uh, another method which will work as a checker whether input is getting matched with the output on the next clock tick or not. So I will just write a method for that. So I will write it as a, and the return type of that should be void because it will only display the message. I will name it compare, and there will be 2 arguments of a single bit logic data type. And inside compare, I will put a if condition, and it's a very simple one. If input equals to the output, then I will just display the test is passed. Else test failed. So it is this simple. So I will go back to my stimulus initial block, and right before applying the another signal to the D-in, I will just go ahead and call that compare method. And the reason I am doing that on the next clock tick is because it will take at least one clock cycle to to get the response from the DUT, or or for the output to be generated. So here, right before applying another stimulus, I will call the compare method, and inside that compare method, I will pass 2 arguments. The one is of course the input, the other one is of course the output. Now it is done. Now I will apply the another input, and since we have already applied 1, this time I will apply 0. and I will repeat it for 1 nagage of the clock so that I can get the response and so that the input can be transitioned to the output. And right after doing that, I will call the compare method again. So I will just copy it and paste it right here. And right after the compare method, our testing is done, and I will just call the stop, which will stop the simulation. So first, let's go ahead and check for any compilation error, whether I have made any typos or not. Okay, there is an error. There are errors. Oh, so silly of me. So when you are using the repeat at some edge of the clock, you also have to mention the at the rate. So at the rate should be mentioned at before any event. So I will just check for any compilation errors again. Okay, this time it's just fine. And now what I will do, I will run the simulation and we will check whether the connection of interface is working or not and all the tests are getting passed or not. QuestaSim test. Okay. Okay, so all the tests are passed and you can see the things that our dollar monitor is printing, the dollar monitor system task. So right here at the 0 time instance, we have applied in this initial block, we have applied t in is equals to 1. And since uh, the reset is asserted for 3 clock ticks, for 3 nagage of clock ticks, it doesn't have any effect in the D out. But reset does affect D out. As you can see it right here that it will assign 0 to D out. So that's why monitor got triggered again because it detected change inside its sensitivity list. So D out turned to 0. But right after that, on the 4th clock tick, when reset is on the 3rd clock tick, when the reset is deasserted, Dean changed to 1, and Dean was 1, so the monitor did not trigger for D in, but D out changed to 1. So it just transition it just gets the input from the D in, and then our compare method came into play, and it sees that that in the next clock tick, D out is equals to D in, so the test was passed. And on the very same clock tick, I applied 0 to D in, which you can see it right here, and you can see it right here that D in 0 has been applied. So it didn't affect D out, but on the next clock tick, D out gets 0. So this interface is working just as fine. So you might not find it that much useful in a case where we have the limited numbers of modules and in our case specifically, there was only a single module. But for some designs, for some large designs, some projects in which you are connecting large number of modules, let's say around 15 or 20 modules, and each of those modules have lots of signals which are not common to each other. Then on such case, if you want to change a common signal that is shared amongst those signals, let's say if you want to change the width or the data type, you can still parameterize it, but still uh, it is more error prone, and interface just solves that. So it works as an intermediary between the design and the test bench. So it talks to test bench on the behalf of the design modules. So coming back to our interface, so this was the generic way of declaring here, generic way of declaring the interface inside the port of the design. So there are other means. So for example, instead of doing this, you could have just directly mentioned the type of the pins to be of the name of the interface itself instead of using the interface keyword. So here I will do that. I will write pff underscore interface. I will save it. So this right here is the explicit declaration in which you are writing, in which you are mentioning the interface name as the type, and the previous one was the generic declaration. So let's find out whether this works fine or not. So I will save the code and I will go ahead and run the simulation. First, I will check for any compilation error. Just a second. Okay, it's fine. So let's go ahead and run the simulation. So I will run. So as you can see it right here that it is working just fine. So first let's quit the simulation. So with the explicit declaration, you could just do more stuff like in this case, we will be using the particular mode port that is direction dir. So I could also mention that particular mode port right here. So if I will mention it right here, I do not need to mention it uh, inside the during the declaration of the instance in the top level module. So I will go ahead and do it. So for that, you just need to mm, write this, and then uh, before that, you have to access that particular mode port, and our design mode port is direction, and then you can mention the user defined name pins because pins is getting used right here. And in the test bench, since you have already selected the mode port in your module declaration, uh, you could just go ahead and remove this from here. This time you just have to mention the interface instance because you have already declared it right here. So let's find out whether this works or not. First, I will check for any compilation errors. Okay, there are no errors. So let's go ahead and run the simulation. So yeah, it is working just fine and it is same as the previous types of declarations. So there are several types of declaration. I mean, the two types of declaration. So in the generic, you just have to write the keyword interface, and you can mention a user-defined name. Then in the top level test bench, you can decide that whether you want to connect to the dir or dir mode port or to the reverse dir mode port. So I would always use the generic one because for most of the projects, I want to customize the connection at the top level test module rather than going through every separate modules. So it's up to you, whatever suits the best for your requirements. So that's all about the basics of interface and using modport to restrict the direction for certain modules. So I hope you find this video useful, and I will be making more videos on interface such as clocking blocks and their usages. So stay tuned for more, and thank you so much.